All right, so we're gonna do a few sample problems today. Just try to keep getting good at this. We got Tigger. Here's Tigger. Nailed it. And we have said that Tigger's like 45 poundish or has a mass of 20 kilograms. Discuss quickly in your group then. See if you can't play this out. Based on yesterday then, roughly what should the spring constant of his tail be? Now this is a guess estimation, but if you do with some small calculations, you can be a little bit more accurate than others. We'll talk about how to do this in just a second. Discuss quickly in your group. What would you guess the spring constant in Tigger's tail reasonably is? Discuss. Take about a minute before we take off.
Yeah, so you don't.
No.
What happened yesterday?
Based on the homework.
No, I don't want the homework. I don't want based on the homework. I don't want you to base off.
Based off to what we did. Okay.
Based off my knowledge on how to do that,
Like 20 kilograms.
Good night. And it feels like every day we're coming in here. Woe is me! Stuff is hard and I don't perfectly get it.
I don't slightly get it.
Okay.
I could not do that.
See, let me check how many emails I have from you on questions. How many times I've seen you for advisory yet, or if you're here on Tuesday.
I can't.
Well, then I guess it's just gonna suck. All right.
It helps if I do my homework before.
Yeah, that'll. Sure. All right. What you got? All right. Here's what you should have done. Okay, because the issue is that like this is a relatively easy thing to do, and if you just get very robotic with physics and not try to figure out like what it's actually doing, it becomes way harder to do stuff like this. This is physics way more so than even the homework is. The homework's practice, but you've got to understand what a K is. Sometimes people try to finish the homework and they don't know, and they don't think it, and they think that they can just launch into it. And the problem is they don't actually have the knowledge. So one thing I'll just drop you on you is if you're struggling doing the homework, it's probably because you don't understand the concepts. If you don't understand the concepts, the homework's probably going to take 4 times longer. That's a rough estimation, but it's probably about right. So make sure that you're reading the textbook. If you don't understand what K is, you're probably not going to use it correctly. What is K? What's K? That's not great.
The relationship between
I can tell you it's
It's how strong a spring is, right? It's roughly how strong a spring is. Now, we learned yesterday how to do this very quickly. The first thing that you probably should have measured is what is Tigger's weight? What is Tigger's weight? What's that? 196 newtons. Or if you wanted to do it quickly, just put that 10 in your head just for a rough estimate, 200, right? Now, when is Tigger's weight going to be equal to his force of spring? Let's pull how?
When
When it's following what? It's first. So in other words, if Tigger leans back on his tail, what should naturally happen? It should compress until when?
1. K equals 1.
No. It should compress until force spring up is equal to his. So the question then becomes, how long would I say his tail probably is? Okay, how big do you think Tigger is? Some pictures of Tigger.
He's 5'2".
That's not, no.
considering the 20 kilograms.
He's a toy.
4 feet tall.
Look up how tall
4,
Tigger
3.
is.
Let's make it easy. Okay, let's say they said 3 feet last up. 4 feet tall is fine, but 3.3 or 3.28 is a meter. So let's just go with a meter, right? Okay, you can kind of look at his tail, kind of get an idea how big his tail is relative to him. Now, obviously, it's animation, so it can sort of change a little bit. But roughly speaking, then, how big would you say his tail is? Sure, 0.7, 0.6 meters. What's up? 0.7 it is. Okay, next question. How far down on his tail, so here's 70 centimeters here, okay, right here. How far down on his tail would you suggest that he probably goes when he's just like sitting there kind of sprung on his tail? Does he go all the way down here?
No.
Probably not. So what would you, it's estimating, but what would you say? What's that? Half, let's go, maybe a little bit less than half. Let's say 30 centimeters. Fair enough? Okay. I think all of you can do this real quick. What's 200 divided by 0.3? Or maybe not in your head, but it was a little bit bigger than 600. What's that? What you got?
666. But
Oh, I don't love that. Well, it's round. We'll go 670. Ah, 6-7. I was not on purpose, but there you go. All right, next. Now, that means, based on what we just did, if he compresses 30 centimeters, then he should just be basically sitting there. So if he wants to shoot up into the air, then what's he going to need to do? Compress even further. All right. So let's look at a picture of him kind of compressing, shooting up in the air. All right. Here we got. Where's a decent picture? I saw one earlier. I mean, I guess that's kind of him more sitting there, kind of like what you were talking about. But what else we got here? Yeah, sort of. Let's see here. What else we got? I thought I had a different picture earlier. I didn't think I changed it that much.
Oh, is
Go
it
down
that
for a
one
second.
right
Oh, there we go. All right. So that's him. What's he about to do? Probably. So he's about to accelerate. Is he falling first and second? Say, based on this, how much stretch? Okay, how much has he been pushed down from his original position? We decided his hole was 70, 30 centimeters down, a little bit more than half would be him just sitting there. So how much would you guess that he's actually down in this point? 50 centimeters. Let's go. He's pretty close to the ground. We'll go a little. We'll say 60 centimeters. Fair? Okay. So here's the question. If his mass is about 20 kilograms and K is 670 and he's been compressed 0.6 meters, find how much Tigger's about to accelerate. You should be able to do that pretty easily on your own. That is a relatively easy problem. Now, if you are struggling on the fact that it is relatively easy, okay, what's the first thing you need to do? Force diagram. What will the second thing that you will need to do be?
I hate myself for this.
That's probably not the best idea.
Okay, so first oh wait, I got this. Wait.
This is probably not necessarily a healthy thing, but I think the biggest flex I've felt like as a teacher over the years is that you'll get students that are like miss every other class in the day because they're dead sick and will still show up to this one because they're like, well, I don't want to miss it. That's more painful.
I would. Yeah,
This class is the reason why I come to school sick.
Hey.
Yeah, I'm not kidding. Like, this class is
That is not very good.
Yeah, I probably shouldn't be as like happy about that as I am, but I am. So they're right.
I pushed through.
All right, you guys do this. I'm gonna find a better picture of Tigger than what I got here. Actually, we'll steal that one I just saw a second ago. Here we go. Windows Shift S.
I'm terribly ill. Or there's a lab.
Come on. See, look at this beautiful drawing. That was pretty. I mean, at least as far as like dimensions are concerned, that's not bad.
I'm math real fast.
Okay. 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 I'm not good with Mary's acceleration. I'm good with this one.
That is the easier option.
It's just so easy. Like,
I never had acceleration so large. Actually, I think
so
I might.
large. Oh, Lord. I'm scared. Oh, wait.
It was. They had it bigger last hour. 10.3.
I kind of didn't write it out.
All right, running through this real quick. Let's start. Here we go. I'm just going to pink. What's force diagram?
Gravity down, spring up.
Gravity down, spring up, should, and this is important for your force diagrams. I will be checking this. I don't look at their size, but I do look at their relative size, so do make sure that you're checking this. Should force spring be greater, equal, less?
Greater.
Definitely greater.
Oh,
Why greater?
because it's gonna go like.
Not just go up. That's not quite what I'm looking for. Accelerate up. Correct. Now, the reason I highlight the go up, accelerate up is you're going to see a problem later today where they do not necessarily match in direction. Remember, sum of forces point in the direction of acceleration, not necessarily which way you're going to go. Now, obviously, if you start from rest, those will match, but if you don't start from rest, they won't necessarily. All right, here we go. What's the next thing that you do then?
Some forces in the Y.
Sum of the forces in the y. Now, instead of keep saying sum of forces in the y, what is that equation just called? Newton's second, yeah. So if you ever want to, like, what should we do next? Newton's second, or Newton's second and the y. All right, and then you got this up here. Same thing we always do. What are the sum of forces in the y?
Force spring minus force gravity.
Equals mass times acceleration. And of course, technically, do we even have to say y here? Not really, because There's no forces in the X. It is all the forces in this case. You would be welcome to just put sum of forces equals MA in this case. All right, next. Let's talk force spring real quick. Just a gentle reminder because some people do this wrong. I told you originally that force spring is equal to negative K delta X, but you'll be reminded that why is that negative there? Delta X, which is kind of dumb because you didn't need that in order to draw the force diagram, right? I don't think any of you in your head went, well, delta X is what should it be, positive or negative in this case? Should it go up or down? So delta X would be compressed, so it would be negative, right? The tail squishes down, and thus the force is up. But you didn't need that, yes? So that's why the AP equation sheet once again does this. Let's just deal with the absolute value. Now I don't need to worry about the fact that delta X is negative or positive. I've got this taken care of. So how do I calculate? Well, for starters, what simple algebra do I need to do to get acceleration? Yeah, just divide by m. There we go. And how do I get force spring? Right. Helpful, not helpful. What's K times delta X based on what we just said? And how do you calculate force of gravity? mg. And of course, yes, 100% plug in those numbers. K was 670 newtons per meter. Delta X is 0.6 meters. Now, I was tempted in the Tigger problem to give you centimeters, but we've got enough to worry about as it stands right now. 20 kilograms divided by G divided by 20 kilograms. And if you plug it all in correctly, I believe you get 10.3 meters per second squared. New question. Is that the acceleration of Tigger, or should I subtract off 9.8 meters per second squared because of gravity?
Whoa.
No,
Yeah, because it's physics. Let's not make it complicated.
You could just like give us.
You already factored
You already
in
figured it in.
Yeah, it's not going to happen. Because I actually believe in your ability to change, but it's not going to change if I change my bar. So I just keep the bar. So moving on. So should I take off 9.8?
No.
No, absolutely not. Why not?
It's already figured in
It's already figured into
the problem.
the problem right here. Gravity is already taken care of. Reminder, what should the force diagram look like if it is accelerating at 9.8? What would Tigger's force diagram look like? Yeah, literally it's going to happen to Tigger in just a second. Once he's up in the air, you're going to have just force of gravity down. So the fact that this spring, when it was even, like we talked about originally, when he was down that 30 centimeters, which helped us figure out what the heck K was, when it was even, you'd have an acceleration of 0. Less than even, okay, if force spring was down here, you'd accelerate downward. But since it's bigger, this extra right here in the picture, that's the sum of forces. And that's what's causing the acceleration upwards. So this is upwards, absolutely. 10.3 should be your answer, absolutely no different. Next, as the spring is being sprung, will the acceleration stay at 10.3? No. Why not?
Because he's not on the ground.
No, hold on. It's as it's being sprung, not. You're 100% right there. Obviously, up in the air, we already talked about force gravity is acceleration will be negative 9.8. Why will it not stay at 10.3? Because delta X is actually getting, as it gets less and less and less. Or here's another way to look at this. Okay, if this force diagram changes, which it would, how? As the spring is being sprung, how does this force diagram change? What's that? Force spring would get less and less and less and less and less until when? It would be 0 when he?
At the top.
No,
Stop.
when he leaves the ground. Once he's up in the air, away from the ground, then it would just be gravity pulling him down. That's, of course, going to stop him in the middle of the air in that particular case. Questions, concerns? How do we feel about the Tigger problem? Okay, there's the math of the Tigger problem, and then there's like these 7 other questions that I asked, because those 7 other questions are a strong indication of if you understand the concepts or whether or not you're just kind of mathing it to a certain degree. All right, next, 2 more problems, and we're done for the day. That'll probably take us the rest of the time. Now, this next problem is meant to be very much review, okay? But we also, I'm going to add like 3 different pieces that I want to put in here, okay? And I want to be very segmented in how we tackle this so that you can look at this and go, okay, that piece I get, this piece I don't, this piece I don't, so we can talk about it a little bit more. Okay, so here's the three things we're going to look at. Number one, I'm going to put an object shooting up a hill. Let's say like a book. Now we're going to shoot it up the hill. How fast are we going to throw that book up the hill?
Okay,
20 meters. 40?
20 meters.
No, not 40. Oh, fine. All right.
Because he didn't want you to take your
I mean, 40 is ridiculous. 100 is worse. 220 miles an hour. All right. Now, next. Based on yesterday, this is a textbook on, let's say, like wood surface that you were dealing yesterday on the ramp. Okay. What would be a decent mu value then?
What do we get? Like,
No, not 2. Oh, I'm sorry. Then I misheard. 0.2 is fine. 0.2 is completely fine. Yeah. You saw yesterday that most of the surfaces you were probably calculating somewhere between about 0.2, 0.3. If you were maybe you got up to 0.4, or if you did deal with something relatively sticky, you might have even hit 0.6, 0.7. Chances are good you didn't break much higher than that because of the surface you got. Now, one thing in the lab yesterday that I wish I would have done, I thought about this afterwards, is I wish that I would have, I had you guys do your shoe. I wish I would have had you do your shoe on the wood and on the table, because it is, the main thing I want to highlight here is just with surface friction, it is the pairing of the two materials, not the one material that decides it. So obviously you sort of see that because you used wood and 3 other materials, but I wish I would have done like the shoe, because you can see this, I think I showed this yesterday. Here's my hand moving back and forth on this table. Here's my hand moving back and forth on this surface. Which one appears to have a greater mu value? Probably the whiteboard in this particular case, based on my hand going back and forth and that particular guy. Okay, so here's the problem. Okay, it doesn't look like we have a lot of information, but here's the problem. We're going to shoot this book up the ramp. Oh, I need one more thing from you. What would you say the angle of this ramp seems to be? 10 sounds perfect. 10 degrees. 10 degrees. All right, so actually, okay, moving on. That's probably not a good move for me to do. Okay, so here's the 3 numbers that you've been given. Here's the situation. We're shooting a book at 40 or 98 miles an hour. Is that right? 40, 45, double 80. Yeah, I think it was like 98. Okay, anyway, 98 miles an hour up this hill. Okay, we're going to say that we have a very, very large amount of space, a very large board, and the question is, how far will this book go before it stops? Okay, so what am I asking? What am I asking for if I ask how far it goes? Delta x, displacement. And actually, without maybe realizing it, I gave you another variable. Velocity final is 0. And we've talked about this a couple times, but just so this is another reminder, is this going to be a one-dimensional or a two-dimensional kinematics problem? One. How come? That is true, but I think, remember I told you there's an easier way to look at it so that you know that. And it's the answer of whether or not it's straight line. Is this going in a straight line the whole time? Yes. Okay. As a matter of fact, you'll notice my velocity is right along that straight line. And chances are good that you're going to see that the acceleration is also along that straight line. Now, this is all the information I have here. Now, you will notice, like I said, there's 3 parts to this that we're kind of working on, and I'll highlight them right now so you can see them. Number 1, you will notice I did not give you mass. I did not tell you what the mass is. That's the first part. Secondly, we have the fact that it is a hill, so we're going to practice a little bit on the hill. And the third thing here is we got kinematics, what I would argue is probably the simplest part of that, but that is the 3 parts that you're regularly seeing in your homework. So that's what I want to do now. All right, so what should we do first? Force diagram. I will give you about 30 seconds to a minute to get out in front of me. Please draw your force diagram. Okay. Appreciate your paying attention at 6th hour on a Friday. Sad that this stuff has to fall when it does. I know. But I still appreciate it. Guten Tag, Senor. ¿Cómo está?
Pretend I'm not.
You're not here.
Ignore me.
I'm switching colors. What am I switching to? Purple it is. All right, what you got? Force diagram.
Oh, right.
Gravity noun.
Normal perpendicular.
Normal perpendicular, so up and left.
And then force of friction back.
Force of friction back which
Down
way?
left.
Down and left, or you could also say, well, that's fine. You can also say parallel to the hill. All right, next. Should we shift the axis?
Yeah.
100% yes. Now, just a gentle reminder, why? When do you know to shift the axis?
When acceleration. When you want acceleration.
You want your direction of the acceleration
Close.
on the
To be
x-axis.
On a axis, but yes, I mean usually you're right. It does fall on the x. Now, again, I want to remind you real quick that there are a couple of problems where this happens, and I feel like the moment I introduce hill problems, anytime any student sees an angle ever, they go, "I'm shifting the axis." Like, okay, you're making your life 10 times harder. So I want to remind you real quick. Number one, let's pretend there's a. Actually, let's do this. Let's go to another page real fast. There's a hill. Here's an object. Here was like a problem that you dealt with before we ever learned about shifting the axis. Here's force gravity, here's some random force horizontal, and here's force normal. But the question was asked, what force is necessary to hold this on the hill? Why do we not have to shift the axis here?
Because there's
You
no
don't want acceleration.
Almost.
You're not
There's no
There is no acceleration. Right. Now, by the way, just as a heads up, you don't have to shift the axis. You can. Now, in this particular example right here, I probably wouldn't, and the reason why I wouldn't is because there's already two forces nicely on the old axes. But what if you had a problem like this? What if instead of pushing it horizontal like it used to, I said, hey, there is a force going parallel to the hill, and it's held in place? Well, number one, there's still no acceleration here, so you don't have to shift the axis. And so, by the way, if you don't, you can get the right answer just fine. But in my humble case, if I was doing this, I would shift the axis, because by shifting the axis, both of the two of these are now going to be on an axis as opposed to one. And in that case, totally your call on which way you handle it, but that's how I would personally do it. Another problem that I'll just remind you of is this. Here's a box that is pushed at a downward angle by whatever random force. Here's force gravity, here's force friction, and here's force. Actually, force normal would be bigger in that case. And why would I not shift the axis here, even though there is an angle in this guy right here?
Because acceleration's already.
Once again, acceleration is going to stay on that x-axis in that particular case. So how do I tell the difference, Spain or between the two of these on a test? Number one, I will tell you that this will be an angle on a force. If it's only an angle on a force, you're probably assuming it's going across the table, or it might even say it's going across the table, so flat surface. This will literally say a 10-degree hill, a 12-degree hill, or more than likely it'll say the surface is 30 degrees with the horizontal, aka there's your angle right there. Questions or concerns on whether or not you should or should not shift the axis? Cool beans, back to our regularly scheduled programming. All right, next. On this situation, which way should you shift the axis and how much? 10 degrees.
Clockwise.
Counter, I believe, if you're
Yeah,
doing
wait.
right, because if here's why, you're going to go
Oh, sorry.
counter in that particular case. We want to get good with clockwise and counter, but it's not perfect right now. Yes, we would shift. Now, that being said, you go, I don't know. Okay, well, here's the simple thing. If you shift the axis correctly, one should be perpendicular and one should be parallel. So the way I would do this is not worry necessarily about which way it shifts, but only draw my first axis straight down through force normal, because that is perpendicular. Now, you'll be reminded about something I told you when you draw your pictures to be careful of, and that is make sure that you're drawing force friction as best you can as perpendicular to force normal as you can, because otherwise it's going to mess stuff up, because now I'm going to draw my other axis parallel to force friction. And the only reason I just highlighted that it was 10 degrees shifted counterclockwise is simply this, that you know that this bottom axis just came over from the vertical 10 degrees. So I'm going to move force of gravity so it's not as much in the way for a later situation. All right. So what are we trying to get with the sum of forces? Jumped out in front of here. What are we trying to go get? Because we're trying to get a variable here, right? We got to. I mean, honestly, why don't we just use kinematics right here? I don't have enough information. How many kinematic variables do I need? 3. So what are we going for right now? Acceleration. Now, of course, acceleration is going to be on the parallel, okay, or x if you prefer, okay. But where do you want me to begin in terms of summing the forces? It's on the forces in the y. Now, why would you start in the y if we're trying to get to the x?
Sort of know.
Oh, sorry, not the y. You keep saying y. Perpendicular. It's fine if it makes sense to you. It's fine. I don't think it makes sense long term, having done this the amount of time that I have. I think that you're more familiar with y, but that doesn't make it necessarily the best option. And I'll come back and talk about that more. Oh, I actually didn't talk about it. Okay, I want to talk about a thing that people screw up on this. Coming back to the force diagram. Here is a thing that people will regularly do that irritates me nonstop and actually kind of speaks to that just a little bit here. Okay. Here's what people will draw for their force diagram, and I will tell you I will take off all the points for the force diagram if you do this. They go, hey, force normal is up, and force friction is back, and force gravity is down and to the left. Do you get to change the direction of forces? No, you get to change how you look at them. Now, I understand somebody that's done this before got irritated at me, and they go, Spainhour, but if I do this, okay, I can still get the right answer. Sure, but just as a heads up, if you haven't noticed this, and maybe you probably haven't because it doesn't seem like this to you, I'm a very lazy person, okay? If this was easier and lazier, I 100% guarantee that I would stick with this as well. But the chances are good that the reason why this is easier for you is you just want to remain with y being up and x to being the side. You want to remain with what's familiar. And the first thing I'm going to say is that doing what's unfamiliar might feel unfamiliar and therefore more difficult, but you need to, number one, being in hard classes, challenge yourself with stuff that is unfamiliar so that you can do better long term. And there's also problems later in this course where this is absolutely the better understanding to get to. So, if you do this second one, just know right now this is a no-go. Do not do this second one. I will be taking off a crap ton of points if you do that, so don't do it. Okay, moving back.
Wait,
Next.
homework too?
What is the sum of forces perpendicular? Force normal. It's entirely along that, so we're good. What else? And what?
Minus force gravity.
In the perpendicular, yes.
Perpendicular.
You already printed that part.
Okay. Is there anything else?
No.
Cool. What is the acceleration perpendicular?
None.
None. That's why we did this. That's equal to 0. So force normal is equal to force gravity perpendicular. How do I get force gravity perpendicular? Well, just a reminder, here's how you draw this triangle. This, okay, this used to be along the old y. Now it's not along the perpendicular. So to get this, I'm going to draw a line kind of up and to the right that is parallel to the parallel and makes a 90-degree angle right here. Thus, this piece of the triangle is force gravity perpendicular. Now, how do you calculate force of gravity?
Mass.
But you go, well, let's say no, we don't know mass. Okay, you would still calculate that way, yes? Leave it alone. How do I get force gravity perpendicular then? Agreed. mg, what's that? Cosine of 10. Why cosine? Because that piece is the adjacent to the 10 degrees. Now, we just found force normal, but we've been trying to get acceleration. Why do we find force normal? Probably to get force friction. How do we get force friction? Now, I don't know force normal, but I know it's this. So this is mu times mg cosine of 10 degrees. Which, once again, we can't calculate yet. Son of a gun. But let's pretend we could. What should we do next? Correct. Sum the forces in the parallel. All right, what are the sum of forces in the parallel? Careful with this, people usually miss one. One they almost always get, but the other they always miss. Negative force friction, that's the one everybody always gets. Force gravity, or x, either one. And positive or minus on force gravity? Minus, yeah. You will notice this is the opposite shift of obviously going downhill. It makes sense to be negative because obviously gravity is harming you going up. Like, think of it like this. Even if this hill had no friction, would it eventually stop? Yes, because of this gravity right here. So, minus force, gravity, parallel. Are there any other forces? So, new question. Is it accelerating in the parallel? Yes, as a matter of fact, it's only accelerating in the parallel. So let's just call that A right there. Cool. A lot of work. Do I know friction? Essentially, what's friction? Okay. How do I get force gravity parallel? Well, go back to our trig. That's this guy right here, right? mg sine of 10. All right. And what's that all equal to? And right here, why didn't you need to know what mass is? Right now it cancels. Mathematically, what are you actually doing?
I'm dividing.
Yeah, you divide my mass across the whole thing. Keep in mind this is very important for later. Every term has to have a mass, right? Every term does have a mass. So cancel, cancel, cancel. Now, let me explain real quickly why, and then we'll finish this problem. Why is it that mass cancels? That's weird. Well, let's pretend for a second that this textbook, we got one textbook and then we got a second textbook. And the second textbook is twice as big. Twice as much mass means what's going to change about the second textbook? Twice as much what? Force of gravity. But if it has twice as much gravity, it's also going to have twice as much. And if it has twice as much normal, it'll also have twice as much friction. So in essence, if we just go to basic Newton's second law, it's going to have twice the forces on it, yes? So shouldn't have twice the acceleration? Except, what does it also have twice as much of? AKA, what other property instead of gravity? What's the other property of mass? Inertia. You're pushing it twice as hard, but it's twice as hard to push, so what effect should there be? None. Just as a heads up real quick, how do I have a hint of when this is going to happen? The answer is simply this. Every single one of these forces up here is mass dependent because it depends on gravity up here. Okay, it's dependent on gravity in some way, shape, or form. Where that won't occur is if you have a problem like this one, because tension is not mass dependent, it's an electromagnetism, and so absolutely mass will matter here. It will never cancel in this particular problem right over here. It'll only happen with stuff like this, like on the hill, or I think the problem we did the other day was the person sliding into second base. Everyone cool with that? Cool. What'd you end up with? The answer is what, negative 0.2. I think this is almost isn't it like negative 6.3? Like 3.63? Yeah, they did this problem like almost the exact same numbers last hour. So no, it was the same numbers. 10 degrees. So yeah, negative 3.63 meters per second squared. And is that the final answer? No, but the solution is relatively simple. Now that I have acceleration, what do I need to do? Kinematics. Vf squared equals vi squared plus 2a delta x. Vf is 0. Nope. Yeah, that's right. So negative vi squared divided by 2a equals delta x. So that's negative, here we go, 40 meters a second squared divided by 2 times negative 3.63. So that's like negative 7.2 on the bottom. That's 400 on top. So what did it end up last hour? I think it was like 14. So 14 times 4, 40, like 56-ish. Is that right? Am I wrong? Not very wrong. Hold on. Oh, it is.
40 squared is 1600.
I'm confused. I got 216.8.
Well, it's not.
I got
That's
220.
I got 220 as well.
220 point something. 39.
Oh, I see what I did. Yep. Okay. Touche.
Wait, did I type it?
Yeah, you're good. You're 100% good. I did 20 squared in my head, not 40. So yeah, 220 squared. 220.4.
Oh my gosh, I thought it.
Or, just a reminder, 1,600 meters is a mile, 400 meters therefore is a quarter mile, so this book just went on a little bit bigger than a 200-meter dash up the side of we have a very long piece of wood in order to make this particular thing happen. Now, other things that could happen on this on your homework. Number one, instead of asking what I did, simply I could have said, hey, the board is 7 meters long. What's the final velocity leaving the board? And then we could do projectile motion or whatever. I also could have given you 3 variables. I could have said, hey, the board is 2 meters long and it stops at the end of 2 meters and it started at 30 and you go, oh, I got 3 kinematic variables. What I would probably ask in that case is not acceleration. I would ask for what's the mu of the material, which of course, if you then calculated acceleration, you would go back to this whole mess, of course, in order to find mu. How to get mu? Well, just like we did yesterday, you need to know force friction, which you would have got from here, because you would have had acceleration, and force normal from there, blah, blah, blah. All right, let's break this problem into a few pieces for the fist of 5 on this one. Fist of 5, your ability to do the force diagram. Cool beans, okay? Fist of 5, how you feeling? Okay, next, fist of 5, your ability to, what was the other one? Sum of forces. Cool beans, and fist of 5, the kinematics on the very end. How you feeling about the hanging around with mass thing? I will tell you, I do this anyway, even if, and you kind of want to get good at that long term, because this is yet again a thing where, like, I'm uncomfortable with this. Yes, but I'll guarantee you, if you get good at this, you will write less. And the really nice thing about doing it this way, honestly, if this is me, I'll be straight with you, I don't plug numbers in here. I still take that equation and I just replace that guy right there. I personally like to do problems such that I just pick up my calculator at the very end of the problem and just have to do it once, and arguably it's a little more efficient that way. All right, questions, concerns? Cool beans, let's do one less problem. We are going to do a situation extraordinarily similar to the first lab, okay? The only major difference is instead of putting it on a frictionless surface like it was with that hockey surface, we're going to say it's on the table. As a matter of fact, this was technically one way that you could have done the lab yesterday for surface friction. You got some object right here on a flat surface. You got a pulley hanging right over here is a second object. Let's say mu of the surface is, let's make it easy, let's say it's 0.5. Give me some mass for number 1. Just make it a nice, clean, easy number. 20? Okay. Mass of 1 is 20 kilograms, fair enough. And give me a mass of 2 that is a nice, clean number, but smaller than mass 1. 10 it is. That's funny. Last hour chose 10 and 5. All right, the question is, how much will this situation accelerate? The major difference in this problem is that you do not have one object, but 2. And thus, there are 2 force diagrams. So we're going to try to go through this pretty quick because I only got 10 minutes left. I apologize for taking the time to do, but let's try to go quick. Okay, so force diagram on the first one. What you got?
Gravity down.
Gravity down. Now, the first thing I'm going to point out is since there are 2 objects, we probably want to distinguish. This will be force gravity of 1. Next.
Normal.
Normal. Should normal be greater, equal, or less? Equal. Agreed. Okay. Next.
Tension.
Tension. Correct. Which way? To the left.
Right.
To the right. Very good. There's tension. Okay. And greater, equal, less. Less. Now, ultimately on this, you might be wrong, by the way. You might be wrong. Maybe friction is bigger. But if you are wrong, it actually doesn't matter because if you solve this, if you expected a positive acceleration, obviously accelerating to the right, and you were wrong, you'll get a negative acceleration back the opposite way. That is correct. All right, now, what's the force diagram on M2? Gravity down. And actually, once again, I'm going to label this as force gravity of 2. And if I was really careful, and I don't necessarily need this, this should be smaller than this one over here. But again, don't worry about that. I'll show you what I need and what I don't care about in a second. And next, what else is on that guy? Which way? Up. Should it be greater, equal, or less? Less. Why should it be less?
It's going down.
Okay, well, a couple more questions. Technically, how should this tension relate to that tension, keeping in mind they're the exact same strain? Equal, because of which of Newton's laws? Third. For every force, there is a equal and opposite force. So I didn't draw it perfectly, okay? I did not make them the exact same size. I don't expect you to either. When you draw these force diagrams, please make sure that the force diagram itself is internally consistent, not necessarily with each other. So absolutely make sure tension is smaller than F2G, and tension here is bigger than that, and just know that they are the same size. Okay, next. Here's the major problem with dealing with multiple objects. Which way do we expect this guy to accelerate? So positive x, yes? Great. Which way do we expect this guy to accelerate? Okay, so that's confusing because technically this should have a positive acceleration and this one should have a negative one, and that's going to mess us up. There's a couple ways to tackle this, but I'm going to give you the easiest because that makes sense. Why wouldn't I? All right, here it is. Who gets to decide which way stuff is? Us. So here's what you do. Whichever way the whole system is moving, that's the way you define as positive. So for this guy up here, obviously that's exactly the same. But for the bottom guy, now we're going to say that it's accelerating, sorry, it's positive this way. So now this is still a positive acceleration. And now this one is also a positive acceleration. Does that make sense? Next, should they accelerate the same amount? Well, let's talk about that. Assume that you drop this off. Would both of them start at the same velocity? So same initial velocity. Should they cover the exact same displacement? Yes, because otherwise the string is either going to break if this one goes further, or it's going to get scrunched up if this one went less. So they're going to go the same distance. Is it going to take the same amount of time for both of them to go that same distance? So they got same initial velocity, same distance, and same time. So are they going to accelerate exactly the same amount? And then the final question, because you just answered that, should they end at the same velocity, or sorry, same speed then? Yes. So they have the same acceleration. So technically that means if I just find one, I got the other, right? All right, where do you want me to start? Let's do that. Let's do 2. Okay. Now, sum the forces how for 2? All right, makes sense. Sum the forces in the y. All right, what are the sum of forces in the y? Don't forget that we changed the direction of positive. Negative tension, positive, force gravity 2. Okay, first piece. Is it accelerating?
Yes.
But look here, this is a dangerous thing. What m is this? 2, correct, because that's the object accelerating. So that's not all the mass, that is mass 2. And actually, let's shortcut this a little bit so we can go a little faster today. Instead of force gravity 2, let's skip a step, which is fine for you to do as well. How are we going to calculate force of gravity of 2? Almost. M2G, yes. So I'm going to write that down. Now I got 5 things up there. How many do I know? Or more importantly, let's try to flip the question. How many of those things don't I know? Tension and crap. We don't know 2 things. If only there was some method we have, there was 2 things that were unknown. What would we do? What would we need to do? Probably, what are you going to need if you have 2 unknowns? You're going to need 2 equations. Same. It's almost like this stuff doesn't go away. All right, where are we going to go for a second equation? You know what? I'm going to make your life easier here real quick. Let's do this for you. Let's get rid of friction real fast. No, I'm not, because I promise I'm making it simpler. I'm going to say that mu is 0, actually. If mu is 0, then how does this change things? There is no friction anymore. And arguably then, when we go to number 1, is there any reason to worry about the y?
No.
All right, so let's go to 1. What are we going to do?
You're gonna sum the forces.
In the... All right. Helping you out here, what is the sum of forces in the x now? Tension. All right, that's it, right? And what's that equal to? M1A. Now notice again, I'm not distinguishing between these A's because as we already discussed, they should be the exact same amount. Also, notice, excuse me, I'm dying. You don't notice that, it's going to happen eventually. At least hopefully more slowly than originally it seems. All right, My two unknowns are tension and acceleration. So I'm looking for a second equation with the same two unknowns. And looking at this equation, how many do I not know? 2. Tension and acceleration. So if you can at least get here, once again, similar to last chapter, out of like 10 points or out of 100% of the points, I'm probably going to take off at max, if you can't finish this, maybe like 2 points out of 10. Okay? Now, one thing I will show you real quick, okay, is that as you look at this, you got your two equations, you do system of equations, you're very used to substitution. But I'm going to show you that there's a way easier option. And it might not appear as easier because this is already solved for t, but if I had kept friction around, this would have ended up as negative mu m1g. It's even more obvious that you should do it this way. Do you remember elimination? People like remember it, but don't even remember what exactly it was. I'm going to briefly describe elimination and when it's way easier. Okay? Elimination works like this. Equal sign means both sides are the same thing. Yes? I don't know what they are, but they're the same thing. I'm going to make something up. Let's say this is 10 and this is 10. Cool? And over here, again, same thing, equal sign. I don't know what they're equal to, but I do know they're the same thing. 5 and 5. Now, while I don't know what anything is this 10 plus this 5 equal to this 10 plus this 5? So can I just add the left sides and the right sides to each other and then still remain equal? Yes. Now you might say, why do I do that? Well, in this particular case alone, you will notice that one of my variables is a negative t. And the other variable is a positive t. So what really nice thing is going to happen when I add the left sides of those equations? Number one, it's going to nicely cancel out that t, and there's another benefit as well. When I do that, let's go ahead and get rid of friction again. What would the only thing left on the left side be after the t? Well, I'll write it all out. Negative t plus m2g plus t, that's the stuff on the left side. That's my 10 plus 5. And the t's cancel, leaving me with just this. What would the right side be? And the other nice thing that this will end up doing is actually putting your variable nicely over on the right side so you don't have to move it around in the slightest. What's the last thing that, well, what's the next algebraic step that we do here? Because we're solving for a. Nope, not yet. You're going to factor out the a in this case so that there's just one a. So I'm going to just factor out a. And now that a is factored out, what are you going to do? Now divide by m2 plus m1. So your final result would be m2g over m1 plus m2 equals a. And if you remember the lab, this is the lab. And you might have remembered that when I put total mass, I had you add the sliding mass and the hanging mass together, and this is the actual reason why, because you have to get their total inertia in that case. But you will notice that this is in fact the sum of forces, which is the hanging masses force of gravity, just like in the lab. Huzzah! We technically didn't learn anything new today. We were just trying to do a little bit better. We'll go over stuff on Monday, test on Tuesday. Off you go.